Okay, so starting off with a quick review of chapter 9, which is the periodic table. Now we haven't reached chapter 9 linear order. We've covered chapters 1 and 2, and after that I skipped forward to chapter 9 before going to chapter 3. Right? And so chapter 1 is states of matter, chapter 2 is atoms, elements, and compounds. Chapter 3 is bonding and structure, and I felt it better to cover the periodic table and get an idea of how the elements are placed in the periodic table before talking about bonding and structure. Right? So that's where we're in chapter 9. So, right, we in the periodic table we've talked about how elements are arranged according to the increasing proton number of the groups and periods. The groups are vertical columns going from 1 to 8, and right, those signify the outermost electrons. Right? So the increasing number of outermost electrons, group 1 has only one outermost electron, which is called the valence electron. Right? And group 6 has 6 outermost, so you can figure that out. Group 8 has 8 outermost electrons, and that is the group where right, all the elements are stable atoms. Right, and that is the exception. So helium is one of the elements in group 8, right? And right, it only required 2 outermost electrons instead of 8 to be stable, and so that is an exception within group 8. But otherwise, all the rest have 8 of them. Okay, then periods are the horizontal rows. They go from 1 to 7, and these signify how many electron shells there are. Right. So as you go right from period number 1 to period number 7, you have an increasing number of outermost shells. Right. So an element in period 5, for example, will have 5 outermost shells, and then right, obviously the corresponding number of electrons. There are certain trends, general trends that we can observe. If we move down a group, right, so the vertical columns, the number of shells, electron shells increases, and that's because when we're moving down a group, right, we're actually moving into the different periods. Atomic size or the radius of the atom is increasing again due to the increasing number of electron shells. And the reactivity changes. Now, it changes differently for different elements depending on which group they're in, right? The reactivity increases down a group or decreases again depending, right? So that's how readily they take part in a chemical reaction. When you move across a period, which is going from left to right, the elements change from metals to non-metals. That's one thing that's happening. There's an increase in the number of outermost electrons, right? So you have one outermost electron in group 1 in a certain period, and then you move across from left to right, and you end up with 8 at the end. And the structure of the elements also changes, right? So you have elements that form giant metallic structures, moving on to forming giant covalent structures such as carbon, right? So an example for a metal is magnesium. And then you move to simple molecular, right? So for example, chlorine, which is diatomic. And then finally, for group 8, you have monatomic gases. Right?
Yes.
Then studying group 1, focusing on group 1, some of the properties are that they're all very reactive. All the metals in group 1, they're called alkali metals, and they are stored under oil, right? And they react as soon as they come into contact with air or water. They are good conductors of electricity and heat. They are soft metals, right? And their hardness decreases down the group. They have low densities, right? You see that lithium only has 0.53 gram per centimeter cube, potassium is 0.86, but there's a trend of the densities increasing down the group. They have a shiny surface when they're freshly cut, They have low melting points, so just 181 degrees for lithium, 64 degrees for potassium, so the melting point decreases down the group, and the reactivity increases down the group. Right, so lithium being at top is the least reactive, and potassium is the most. Now, the reason we are giving only lithium, sodium, and potassium is because those are the commonly available that you can possibly have in your school laboratory. Obviously, the other elements, but those are not commonly available or they're radioactive, right? And so those aren't discussed. But the trend is the same. If you look at an element that comes after potassium, it's going to be more reactive than potassium, right? And the reason for the increased reactivity is as you go down the group, the size, as we talked about, the size of the atom is increasing, and so the valence electron is further away from the nucleus. So the nucleus has protons which are positively charged, and the electrons are negatively charged. So there is an attraction between the positive and negative charges. But the further away the valence electron, the outermost shell is from the nucleus, the weaker the attraction of the negatively charged electron to the positively charged protons, right? And so in case of group 1, these take part in ionic bonding where the electron is lost. So we'll talk about bonding after this chapter. And so it becomes easier to lose the valence electron, right? Because the attraction to the positive protons in the nucleus is weaker. Talking about chemical properties of group 1, right? These metals react with oxygen or air to form white oxides, and they burn with characteristic colors. So lithium, right, this is a balanced equation. Lithium reacts with oxygen to give lithium oxide, right? It's white lithium oxide, and the color lithium burns with is red. Metal oxides, then the second chemical property, the metal oxides, right? So what you got over here, react with water to form alkaline solutions of metal hydroxide. Right? So you've got lithium oxide, you've got water, and you've got lithium hydroxide as the product. Then these metals can also react directly with water to give alkaline solutions. So you're getting the metal hydroxide, but the reaction is slightly different. If the metal is reacting directly with water, then you will get an alkaline solution of metal hydroxide, and hydrogen gas is also produced. So you've got potassium reacting with water to form potassium hydroxide and hydrogen gas. These metals react vigorously with halogens to form metal halides. Right, so halogens are the elements in group 7, and so right, they require just one electron to complete their shell, so they're the ones gaining electrons, and the group 1 metals are the one losing electrons. Classic example is sodium and chlorine, right? So the two of these react to form salts, in this case sodium chloride, which we are very much familiar with as the regular salt that we use, table salt. Right. As we talked about, the reactivity increases down the group, and I mentioned the reason why that happens, and that's stated over here. Right, group 2 is pretty much the same. Right, the properties and chemical properties of group 2 are pretty much the same. Group 7, right, are called halogens, and those include fluorine, chlorine, bromine, iodine, and there will be a focus on chlorine, bromine, and iodine because these are the elements that are easily available and something that you would be able to work with in your school lab. They are colored, and the color becomes darker down the group. They exist as diatomic molecules, so right, the symbol for fluorine is F, Cl for chlorine, Br for bromine, and just I for iodine. And you can see the two, right, so they're diatomic, the two atoms of these joining together to form the molecule, the elemental molecule. At room temperature and pressure, they go from gas to liquid to solid, right? So you've got gases, liquids, and then a solid. Right, so chlorine is a gas, bromine is a liquid, iodine is a solid. And that is because the densities of these elements are increasing down the group. that is the reason behind it. Okay. Now coming to the chemical properties, they form molecular compounds with other non-metallic elements. Right, non-metallic elements. For example, hydrogen chloride. And so, right, the reaction goes this way, right? So the react with hydrogen form hydrogen halides, which can in turn dissolve in water to form acidic solutions. So, right, first you've got hydrogen gas and chlorine gas, and the two of them react to form hydrogen chloride gas, or HCl gas. Then that HCl can dissolve in water, form aqueous hydrogen chloride, right? So that this is actually a dissolution. It is not a chemical reaction, right? It's just the hydrogen chloride gas dissolving in water. And right, we learned later that it will then dissociate into positive hydrogen ions and negative chloride ions. And then finally, right, the point that we've reached in this chapter, these halogens react with metals to produce ionic metal halides. An example given is iron 3, right? So that's the oxidation state of iron, that's a transition metal, so it can exist as either iron 2 or iron 3. And we come to that today. Reacting with chlorine to form iron 3 chloride. So the balance reaction for that is, right, we've got two molecules of iron reacting with two atoms of iron, reacting with three molecules of chlorine to give you two molecules of iron 3 chloride. That is the review of chapter 9 that we've done so far. Any questions from anyone in class?
Yes, no, sir.
Right, Ibrahim and Fatima, any questions? I know it's just a review, right? But still.
Yeah, I don't have any questions.
Okay. So continuing with group 7, right? There's something that is, unique that's happening with group 7, and that is displacement reaction. So we just talked about the fact that these halogens can react with metals to form ionic metal halides, and this was an example of chlorine reacting with iron, which is a transition metal. But for example, you have, right, potassium iodide, and so, right, you've got potassium, and that is reacting with iodine. Balance this out. Now, what happens is, for example, if I react this potassium iodide with chlorine gas, right? So I take potassium iodide, right? It is aqueous, and I react it with chlorine gas. What I'm going to end up with is potassium chloride and iodine. Right? The iodine is also going to be aqueous as well as the potassium chloride. And to balance this out, now, why did this happen? Well, similar experiments were carried out, and again, our focus is on chlorine, bromine, and iodine. Right? So iodine is actually the fourth in the list because we are not considering fluorine, which comes first, but it is there. Right? And so chlorine is higher up the group than iodine. So the observation made is that a halogen, right, higher up will displace, right? In other words, remove, right, a halogen lower down. And the reason for this is because the reactivity of the halogens decreases down the road. So when you have a metal halide and you introduce a more reactive halogen over there, then right, because it is more reactive, it will take the place and form a new metal halide and displace or remove the one that is less reactive. The question is, why is the reactivity decreasing down the group? And please, right, if you have any question during the class, you can just ask. Now, just for a comparison, when we talked about group 1, right, down the group, the atomic size is increasing. Right? And so the attraction between the protons and the electrons is becoming weaker. And so it was easier to lose the electron for the group 1 metals. Now in group 7, the reason is also the increasing atomic size. So down the group, the atomic size is increasing. Right? And because of that, right, so for group 7, they're the ones accepting electrons. Group 1 was the one losing electrons. These guys are the ones that are accepting electrons. Right, so they have 7 electrons in the valence shell or the outermost shell. Right, and they need one more to have a stable shell, right, 8 outermost electrons. So it is easier to accept an electron than to lose 7 of them, right? Because if theoretically you lose all 7 of them, then your one shell less, and then the shell before that will have 8 and will become stable, right? So they want to achieve a stable electronic configuration. But obviously, losing 7 electrons is going to need far more energy as compared to gaining just one, right? And so that's what they do. And so, right, the attraction, right, there's an attraction between protons and electrons, but because of the, right, increased atomic size and the more shells, right, so there are more electron shells. In this case, right, chlorine has 17 electrons, and so the right electronic configuration is 287, and it has 3 shells, whereas iodine has 53 electrons, and the electronic configuration for iodine is 2, 8, 18, 18, and 7. That's 7 the outer. You can see you've got 5 shells, and so the atomic size is bigger, right? The outermost shell or the valence shell, right, is further away from the nucleus where the protons are, and so the attraction, right, of the positive protons to the negative electrons is weaker.
Okay.
Right, that's one reason. Another reason is, right, the larger atom, right, has a lot more electrons. right? So 53 as compared to 7, that's a lot more, right? And so what they do is that all these electrons are negatively charged, and so they actually repel the incoming electron, right? So they're not very welcome. Just because there's already a lot of negative charge over there, they repel the electron that's coming in to form the stable shell. And the more electrons they are, the stronger the repulsion. And so, right, the less reactive that particular element is, right? The lesser the number of electrons, not only is the atomic size smaller, and so the effect of the positive protons to attract the electrons is greater, but right, the repulsion from the electrons is also lesser, and that makes it more reactive. That is the reason why the reactivity decreases down the road. Any questions?
No, sir.
So in the displacement reaction we did, you notice that, right, iodine goes from, being in a molecule to going into its elemental form. And so at this point, right, it has gained an electron, right? When it reacted with potassium, it gained an electron, right? And so, right, if chlorine is taking its place, it will technically have to lose that electron gain. And so what's happening over there, right, if I just write it out, in the potassium iodide, you have, right, two ions, right? So you talk about ions. Ions are what are formed when an atom loses or gains electrons. If an atom is losing electrons, that means there's less negatively charged particles in the atoms compared to the positively charged particles, and so the ion is a positively charged ion. If the atom is gaining electrons, and so the number of electrons is more than the number of protons, and so the overall charge is negative. And because iodine has gained electrons, right, it is negatively charged. And there are two atoms of iodine involved in the reaction, right? So you've got two of those, and then you've got chlorine gas, right, which is diatomic gas. So this one has no charge at the moment. And what happens is that it goes, right, there's a displacement, and so you've got two atoms of chlorine, and now they are the ones that have taken up the electron, and iodine goes back to being diatomic without charge, right? And so oxidation number is what we call, right, how many electrons are gained or lost. So over here, right, the oxidation number for iodine is -1. It's -1 because each atom is gaining 1 electron, right? There are two atoms that is separate. That will not affect the charge of the ion, right? The charge of each ion is -1. And chlorine has no charge. And over here, right, chlorine is now -1. It has gained electrons, and iodine has gone back, right, to having no charge. So at this point, right, gaining electron is called reduction. We've covered that in earlier chapter, right? So the iodine is reduced, and right, because it loses an electron, each atom loses an electron, then forms a diatomic state, diatomic molecule, the elemental state, right? And so in the process, it has oxidized, whereas the chlorine has gained an electron and it has ended up being fixed. Okay.
Yes, sir.
So, right, this is also an example of a redox reaction. Right, and a redox reaction, I think something that we've covered in earlier chapters is right, a reaction in which reduction and oxidation both are taking place, and that's what we can see over here. There's a color change associated with this as well, right? The metal halide is colorless in aqueous solution. Right, so this is aqueous and this is a gas, and this is aqueous and this is a gas. This is right, so the metal halide is colorless, whereas the chlorine is green in color. And when the chlorine forms the metal halide, so potassium chloride, that goes to colorless. So there are color changes involved, right? And iodine is produced, elemental iodine, and that is orange brown. And these color changes can actually be used to carry out and experiments for displacement reactions. You see a color change, and so you understand, okay, fine. So first it was green, and so there was chlorine in there, right? And now it's turned to brown. That means the iodine has been displaced, and that's why the colors turn brown, right? The metal halide will be colorless in solution, so you won't be able to detect that. Any questions?
No, sir.
Just a minute.
No.
Yeah, any question?
No.
So far so good. Moving on. Right, next we are going to talk about group 7. Sorry, group 8. We just finished group 7. Right, and these are called the noble gases. And the reason they're called noble gases because they are very unreactive. And the reason why they're very unreactive, we've talked about the trends of the groups, right? There's increasing number of valence electrons or electrons in the outermost shell. And except for helium, which has only 2, all the other elements in this group have, right? So all the elements have 8 outermost or valence electrons, right? And that, except for helium, right? Helium has 2 because it only has the first shell, which can accommodate for just 2 electrons. And right, that is the stable configuration. Alright, so having 8 outermost electrons is what the atom wants. It is stable, and as we talked about the reactivity, the reactivity is basically because the elements have incomplete outer shells. Whether it's just 1 electron or 3 or 5 or whatever it may be, as long as it's not 8, it will be reactive. How reactive, that's a separate matter, but it will undergo reactions. These have 8, so that is the stable configuration, so they have no need to react, right? They're very chill. In fact, right, no, right, naturally occurring, right, compounds have been found. They've been made artificially, but right, not naturally occurring. So some of the properties of the noble gases, right? First of all, right, they're all gases and they're all colorless. Secondly, they're monatomic. Right? That means that, because they have a complete outer shell, they're not reacting. Like, for example, right, the halogens, they needed just 1 electron, and so on their own, they are diatomic. right? These guys, they are simply helium. Yeah, go
Sorry
ahead.
to interrupt. Yeah, did you say that they're diatomic, right?
The halogens are diatomic. The noble gases are monatomic,
Okay. Okay.
right? So you've got helium or argon or neon, right, or any of these, and right, that's how they are, right? They're not He2 or He4 or anything else, right? Because again, right, the hallmark of these guys is that they have stable electronic configurations. Then, right, so monatomic gases mean that they exist as individual atoms, and I already mentioned that they are very unreactive. So I did mention that, right, some compounds have been produced, right? They're not naturally occurring. And an example of that is xenon hexafluoride. So xenon is one of the noble gases, right? It shouldn't react, but under laboratory conditions, they have made something like this. They've reacted it with the halogens and managed to produce, right? So this is obviously artificially occurring. Right? It has its uses, right, and whatever, but you know, right, the main points stay. All right. Because they're so unreactive, they have a lot of uses, right? So if you remember way back when, there used to be tungsten lamp bulbs. Has anyone seen those old bulbs that used to glow yellow? They had like a wire, very thin wire going in them,
No, not
Yes.
really.
right? So the tungsten bulbs, right? If I can just pull up a picture, show you very quickly. All right, so I showed you the tungsten filament bulb, right? You guys recognized it. So, right, electricity is passed through it to produce light. Now, not going into the physics of it, the bulbs are actually filled with argon, which is the noble gas, right? Because it's unreactive, and that is so that, right, the tungsten does not react with air. Because if there's air in there and you've got metal and you're providing energy to it, it's very likely that it will react with the air to form some compound, right? An oxide. And so that would, it wouldn't work as it should, and it could be explosive because we're passing electricity through it, right? So there's heat, and it wouldn't end well. And so argon is used to keep the environment inside the bulb unreactive. So, right, these things have their uses. And then another example is neon, right? So you've probably heard of neon signs,
Yes.
right? So the advertising lights, right, or the signboards of shops, right? Now perhaps they've moved to using LED lights or something, right? But the very bright, flashy colors, right? Perhaps they still use some cases today, right? Neon was used, and so electricity was passed through, right? And that's what gave it the fluorescent glow. And the color was basically the color of the glass or the plastic covering the tube light or the bulb or whatever form of lighting it was. Okay, after that, we are going to move on to transition metals, right? We're probably going to complete this chapter today. Okay, any questions before we move on to transition metals?
No.
No.
Okay. right? So transition metals. Transition metals are the chunk of metals, right, that are shown separately in the periodic table. So if I just show you the textbook, okay, and moving to the periodic table, it's better in the chapter itself, sorry. So it's highlighted, yeah, there you go. And so this is the modern periodic table. You can see over here, right? Between groups 2 and 3, this yellow chunk over here, not the one down below, right? Between groups 2 and 3, you've got this yellow chunk, and all of these, as you can see, labeled over here are transition metals. Okay, and you've got some well-known ones over here, for example, titanium that you may have heard of, chromium, iron, cobalt, copper, zinc. Right, so some of the metals that we do hear about: mercury, gold, right, silver, right. So the precious, some of the precious metals as well. They're all transition metals. Okay. So moving back. The whiteboard. All right. Okay, so right, as I mentioned, the transition metals contain a lot of the metals that we are familiar with. For example, iron. Right, so the symbol for that is Fe. Copper, right, Cu, and gold, right, Au, zinc, nickel, all of this. And right, we're going to talk about some of the properties. So compared to other metals, we'll talk about the group 1 and group 2 metals, they are less reactive. That doesn't mean that they don't react. We've got lots of reactions happening with these guys, right? But just comparatively, they are less so. Okay, and when they do react, they form brightly colored compounds. Right, so you've got red, orange, green, all sorts of. Achha, one thing that they're perhaps better at is that compared to groups 1 and 2, right, they are harder and stronger than group 1 and 2 metals. Also, they've got much higher densities. Right, again, compared to groups 1 and 2. They also have high melting point. So the group 1 have lower melting points. These guys have high melting points. With the exception of mercury. Right, the symbol for that is Hg. Right, and so this is the only metal that is a liquid at room temperature. Right, so that is an exception. Otherwise, they have high melting points. They are good conductors of heat and electricity. Right, and this is something that you would expect of metals. Right, and so copper is used in wiring. Right, the other metals that are used as well, but the primary, the best thing, the most economical, right? So there are various reasons why, but copper, right, is the transition metal, and that's the one that is used in wiring, right? Sometimes aluminum is also used. Obviously, it's not as good, right? And aluminum is not a transition metal, right? So, right, copper, so good conductors of heat and electricity, and right, you have, for example, your utensils, your pots made of right copper or something, right, to put food in, and so they need to conduct heat and go. That heat should reach the food that's being cooked, right? And so they're good at that. Okay. Now something is that right they show good catalytic activity.
I have a question.
Yeah,
You said that these metals are in chunks, right?
chunks
As in, you said that these metals are harder than group 1 and 2.
harder as in physically, right?
Okay,
The group one that we talked about, right? So we just go back. So these are soft metals, right? We talked about the physical property of group one metals. These are soft, right? And I mentioned that sodium, you can cut it with a knife. They're that soft. They are metals, right? And the hardness decreases down the group. Compared to those, these guys are hard, right? So if you've encountered copper, right, copper wires or iron, right, or gold, right, so you probably have a piece of jewelry, and I'm pretty sure you won't be able to cut it with a knife, right?
so what makes these metals much harder than the other two?
Well, they're
Is it because of the density? You said they have much more density.
well, density is mass upon volume, right? So that's how heavy they are per unit volume. Uh, it is their how they arrange, right, the metallic structure, and so that is something that we will cover when we do the next chapter, chapter 3, bonding, right? And
Yeah.
so
Okay.
it's how they're arranged inside the metallic structure, and also the electronic configuration and all those factors which make them right harder physically. Okay,
Okay.
and the
Yeah.
densities, right? So higher density, we know that right from physics, just covered that recently. Density is mass upon volume, and the
Yeah.
mass, right, the
Yeah.
atomic mass, right?
Yeah.
And so, right, whatever volume we have, and right, I mean, the atomic masses are higher, and so if you've got a piece of metal, right, you weigh it, it will give you a certain mass, and then you can measure the volume of that piece of metal easily, right? And so when you get that, these guys have higher density. Okay,
Okay.
coming back, uh, they have good catalytic activity, right? And for that, I need to talk about what catalyst is. Do you guys know what a catalyst is?
Yeah, it speeds up chemical reactions.
It takes part in chemical reactions. Is that what you said?
I said it speeds up
Speeds up,
chemical reactions.
right? A catalyst is a substance that speeds up chemical reactions, right? And also remains unchanged, right, at the end of the reaction. And normally how it speeds it up, just to give you an idea, not going into detail, is that it brings the reactants, whatever they are, closer. Right? And so when the reactants are closer, it's easier for them to undergo the reaction, and so that speeds it up. It also lowers the energy required for the reaction, etc., etc. So it has its benefits. And so, right, these transition metals show good catalytic activity, and so they are used as catalysts in industrial processes. Right? For example, iron page, right? So iron is used as a catalyst in the industrial production of ammonia gas. Of ammonia, right? And that is something we will cover later on. It's called the Haber process, and that's just an example of it being used as a catalyst. And right, they do not corrode very quickly. Right, so that's another property. They do not corrode quickly. Right, so the corrosion takes place when the metal reacts with, right, air, basically the oxygen in the air, or water. Right, so if you've ever seen iron rusting, that is corrosion. And other metals also form rust. So if you've got a piece of silver jewelry and you see that it's blackening, right, that's actually, rust for that silver. Okay.
Okay.
So, right, it doesn't happen very quickly. It's not that they don't corrode, they don't corrode as quickly. Right. So those, and then, right, the hallmark basically of transition methods, right? So we haven't talked about that. We have time. We have a few minutes. Actually, I don't have a class after this one, so I think I can, right, wrap up transition metals, perhaps the chapter. Do you guys have time?
Yes, I do.
Okay. Right. So the hallmark of transition metals is that they have, where do we put this? Sorry. Right? They have variable oxidation numbers.
Um, you I have a question. Yeah, you said that for the iron they do not corrode quickly. Is it because they are used as catalysts, right?
No, those are two different things.
Okay.
They can be used as catalysts. That's one of the uses of transition metals. And the fact that they do not corrode as quickly as other metals, that is another property. So they are not, right. And we can understand that from the very first property we talked about, that they are less reactive than other metals, right? The more reactive a metal is, the easier it will react with the oxygen in the air or with water. And that's why if you go back to one of the properties that we talked about, group 1 metals, the alkali metals, they are super reactive and they have to be stored under oil, right? So if as soon as they come into contact with air, they start reacting, right? And if you put them in water, it is a very violent reaction. Okay, so
Okay.
these guys don't react that, right? So because they're less reactive, that's why they don't corrode as quickly when they are in contact with air or water. They do, because we have seen iron rusting. We do see that black coating on silver over time, and that's why, right, rust-proof coatings, or galvanizing, that means coating one metal with another metal. So that's a process, right? Or making alloys. So that's combining two metals. So all of these processes, right, also exists to make these transition metals stronger, and even more rust proof. So stainless steel, right? Stainless steel is basically an iron with a coating or an alloy, right? And so, right, it's not that stainless steel does not rust, it just doesn't, it takes very long for it
Okay.
to possibly
Yeah.
rust, right? So it's not 100% rust proof still, but you can delay it. So it has a much longer life as far as corrosion is concerned.
Okay.
Okay.
Yes.
Okay.
Mm.
Now the variable oxidation numbers. What do we mean by that? Okay. So the oxidation number is, right, how many electrons can an element gain or lose, right? And so that is related, right, to the valence electrons, or the electrons in the outermost shell, right? So
Yeah.
the oxidation number, let's put a hash over there for number, right, is how many electrons can an element gain or lose. Now, since these guys are metals, right, these are the ones losing electrons,
Okay.
right? And so they will have an oxidation, right, a positive oxidation number. So +3, for example, right, they're losing 3 electrons, right? Now, the
Yeah.
fact, right, if we go back and for, yeah, this reaction of metals with halogens to form metal halides, I gave the example of iron 3. And I told you iron can exist in 2 different oxidation states, that's 2 and 3. Right, so that is one example. Right, so,
Okay.
right, iron can be iron 2 or iron 3. That means it can either lose, right? So it can either be in the +2, so it will be Fe +2, or it can be losing 3 electrons, so Fe +3. Right? Now, why this happens is beyond the scope of your syllabus, right? And so electrons move between, their orbitals and gain energy and etc., right? So it is not part of your syllabus, but this is something that happens. So an example is iron, which is, right, we put iron 2 and iron 3. You have copper, right? So it's Cu, and that can exist as copper 1, right? So just +1 or Cu +1, okay? Or just Cu1, right? Or just Cu plus in front. You don't need the 1. If it's just a single plus sign, right, that means the oxidation state is 1. Right? And you
Okay.
can have copper 2. Right? So it's losing 2 electrons, right? Cu plus 2. And so that makes a difference on the kind of compound they form. Right? Iron
Okay.
can, right, and this is, right, it can form iron 2 oxide, it can form iron 3 oxide.
Yeah.
Okay? Or for example, right, copper 1 oxide or copper 2 oxide. Okay? Now,
Okay.
I'll stop here. There's a certain thing I want to bring your attention to, right, which are these numbers, and if you've guessed, they are actually related to the oxidation numbers of elements, right? If you can make that link.
Yeah.
Otherwise, right, we'll continue this in tomorrow's class, right, because, right, we're at the end of the class time, and this will take a bit more time, right, than I was expecting. So I don't want to leave it
Yeah.
halfway, although there's not a lot left, but still. Right, so
Okay.
any questions?
No, sir.
Right, Fatma, Ibrahim, anything?
No.
No.
All right, then I'll see you guys. Right, I'll see you guys hopefully right in the next class. And Sylvia, I'll see you tomorrow.
Okay, yeah.
Okay.
Yeah.
All right then.
All right then.
Okay, Allah Hafiz.
This
Allah.
Allah Hafiz.